All right, let's get into it. You know how you pull out your phone and Google Maps just knows where you are? Ever wonder what it takes to give that same sense of direction to a robot? I mean, from scratch. How do you actually teach a machine not to get lost?
And that is the fundamental question. In robotics, they call it localization. And it's not what you might think. It's not about planning a route from A to B. It's way more basic. It's about the robot just waking up, turning on in a room, and having to figure out all by itself, where am I right now?
And here we have it. This is the robot's world. A simulated room. Pretty simple, right? Just some walls, a few pillars. But for our little robot, this room is its entire universe. And its one mission is to figure out its place in it. A task that you're going to see is way harder than it looks.
So let's start at the beginning. The first attempt. You'd think you'd start with a map, right? Well, they did. And guess what? The robot was still totally, utterly lost.
See, the developer started with a pretty standard tool in robotics. It's called AMCL. It uses a 2D map from laser scans. Now, AMCL is actually great, but only after the robot already knows where it is. There's the catch. When it first boots up, it's clueless. It has absolutely no idea. It needs a person to literally point to a spot on the map and go, hey, you start here. Without that little push, that manual hint, it's completely flying blind.
Okay, so plan A didn't work. What's the next logical step? Well, you give the robot some eyes, right? Let it use a camera to actually see its world. And yeah, that helped, but it also opened up a whole new can of worms, a much, much weirder set of problems. So in the first version of this simulation, every single wall was identical, just plain black. And this creates a tricky problem that engineers call perceptual aliasing. Basically, it's like being in a hall of mirrors. The robot would see a black wall and have no way of knowing if it was this black wall or that black wall over there. It would see one thing, get confused, and match it to a totally different part of the map just because, well, it looked the same. And this is where we get this fantastic quote from the developer's notes. The robot didn't just make a mistake. It wasn't just off by a little bit. It, quote, hallucinated its position. How wild is that? It would be so sure, so confident that it was on one side of the room, when in reality, it was clear across on the other. It was literally seeing ghosts in the machine. Okay, so the developer thought, easy fix. Let's add some color, make things more unique. But the robot was still getting confused. And the reason why is actually super interesting. You see, most vision algorithms, the off-the-shelf kind, they look for things like unique textures or sharp corners to lock onto. But these pillars, they're perfectly smooth, solid-colored cylinders. So when the robot sees the edge of a pink pillar, it looks exactly like the edge of any other pink pillar. No unique features to grab onto. So back to square one. So at this point, you can imagine the frustration, right? And that's when a shortcut appeared. A really tempting one. A way to fix this whole mess, like, instantly. But it came with a catch. And that shortcut is called April tags. The easiest way to think about them is like QR codes, but for location. You just stick these things around the room, the robot's camera sees one, and bam, it knows exactly where it is, down to the millimeter. Problem solved, right? Well, not so fast. The developer actually said no to this idea, and for some really smart, practical reasons. I mean, first, you'd have to physically change the environment, plastering these tags everywhere. Not exactly elegant. Plus, what happens if a tag gets dirty or faded or someone rips it off the wall? The whole system could just break. It's just not a professional, scalable solution for the real world. And this right here, this decision, it gets to the heart of the whole project. It wasn't just about finding a solution, it was about finding the right solution. The philosophy was simple. A truly intelligent robot shouldn't need us to put up signposts for it. It should be smart enough to navigate the world just as it finds it. So, that was it. Time to ditch the standard off-the-shelf stuff and build something from the ground up. Something totally custom. It was time to give the robot a new way of seeing. And the new plan was just elegant. So simple. When the robot turns on, it just does one thing. A slow, 360-degree spin. That's it. And as it spins, it makes a list of every colored pillar it sees. Once it sees a few of them, it can measure the angles and distances and use that info to triangulate its exact spot on the map. Genius. And check this out. It actually worked. This table right here is the proof. This was the first big win. Now look, the prediction isn't perfect yet. You can see there's still some error. But, and this is the key, for the very first time, the robot figured out where it was automatically. No human help. This was a huge moment. Okay, so it's working, but it's not perfect. How do you go from pretty good to pinpoint accurate? Well, the developer dug into some academic papers, and that's where they found the idea that would become the real game changer for this whole project. The big idea is something called a geometric fingerprint. And here's the magic trick. The robot stops caring so much about the individual pillars themselves. Instead, it starts focusing on the relationship between the pillars. The specific angles and distances between them create a totally unique pattern, a signature for that one spot. The best analogy? It's like navigating using the constellations. The individual stars are just points of light, but the pattern they make, Orion's belt, the Big Dipper, that's what tells you where you are.
So imagine the robot is standing in one spot. From there, it creates its own little constellation of pillars. It might see, for instance, that the purple pillar is exactly 71 degrees to the left of the cyan pillar, and the green one is a certain distance away. That specific geometric pattern is like a fingerprint, and it's totally unique to that one spot on the map.
And here's what that looks like under the hood. The robot takes that visual constellation and turns it into a string of data. Basically, a list of colors, angles, and distances. That is the fingerprint. Then it just has to compare the fingerprint it sees right now to a giant database of all the fingerprints it calculated beforehand. When it finds a match, boom, it knows exactly and instantly where it is. All right, so the core system is now super accurate. We're in the home stretch. The last step was basically a big bug squashing session, a rapid-fire hunt to iron out the last few kinks and make the whole thing rock solid. First step was a funny one they called the gray ghost. Sometimes the robot would see a colored pillar, but it would also see the plain gray wall behind it and mistake that wall for another pillar. The fix was pretty clever. They just taught the robot to filter by shape. Basically, ignore big, flat gray things and only pay attention to objects that are tall and skinny, things that actually look like a pillar. Then there was another bug, a logic glitch that was kind of funny. You'd give the robot a destination, and sometimes it would immediately go, "Done, I'm already there," before it had moved even a single inch. The fix for that one was easy, just a simple distance check. It couldn't declare victory unless it was actually, close to the target. And the last bug to squash was the restless robot. It would just kind of jitter in place. Its position estimate would flicker back and forth by tiny, meaningless amounts. The solution for this was something called an update deadband, which is basically just telling the robot, hey, chill out. If the change is super, super tiny, just ignore it. And that made its final position solid and confident. So there you have it. After all of that, the failures, the hallucinations, the breakthroughs, the robot can finally, reliably find its own way in its little world. It's a pretty amazing journey, going from completely lost to having this precise, automatic sense of place. And it leaves you with a really big question, right? We've seen what it takes to master one simple room. So what's it going to take to build a robot that can navigate our world? The big, messy, complicated real world?